It seems like every day the apps we're building are just getting more and more data heavy.
It's true.
And everyone's scrambling, trying to figure out how to handle it all, how to make it faster, how to scale things up without everything crashing down around us,
Right.
and how to make sure it's all super reliable.
Absolutely. Keeping everything running smoothly is key.
It's like a constant juggling act, really.
It is. It's a lot to manage.
Well, today we're diving deep into a platform that's designed to help us win that juggling game. Hazelcast.
Sounds interesting.
We've gathered a whole bunch of information about it, all about its features, its capabilities, how it works,
Oh, okay.
and we're going to take it all apart piece by piece to really understand what makes it tick.
Excellent.
Now, our listeners are a savvy bunch. They know their way around data and tech.
Yes, they keep up with the latest trends.
So we're not going to spend all day going over the basics.
Right.
Instead, we're going to jump right in, get into the nitty-gritty, and see what Hazelcast is really all about. All right, let's kick things off with the fundamentals.
Okay.
It's described as a distributed in-memory data store.
Mm.
So what does that actually mean for someone who's wrestling with these data challenges?
Well, imagine this. You've got a ton of data.
Right, a whole mountain of it.
Instead of keeping it all crammed onto a single computer, Hazelcast lets you spread it out across a whole bunch of machines.
So it's sharing the load.
Exactly. These machines all work together as a cluster. And here's the cool part. All this data lives in the computer's RAM, its main memory.
I see.
So accessing it is lightning fast, way faster than reading from those old school hard drives or even SSDs.
Makes sense.
Now, according to what we've got here, Hazelcast can scale up massively.
Oh, wow. How big are we talking?
You can have hundreds, even thousands of these interconnected machines working together.
That's a lot of horsepower.
It is. It's designed to handle some serious data workloads.
I'm impressed. And it's also described as fault tolerant, which is really important.
Yes, reliability is key.
So how does it make sure we don't lose all our precious data if one of those machines decides to take a nap?
Well, Hazelcast is clever about this.
How so?
It makes backup copies of your data, see?
Okay.
And it stores those backups on different machines within the cluster.
So if one machine goes down, the data's safe on another one.
Exactly. The system just keeps chugging along, no problem.
That's a huge relief.
It is. You don't want to lose all your hard work.
Definitely not. Now, I see here that there are two main ways to set up Hazelcast: embedded and client server.
Deployment options.
Can you walk us through the difference between those two?
Sure. So with an embedded setup, your application code and the Hazelcast software, the part that manages all the data and services, they all run together in the same process.
Okay.
Like within the same instance of the JVM, if you're using Java, for example.
Got it.
The big advantage here is low latency.
Because it's all happening in the same place.
Exactly. Your application can access the data super quickly because it doesn't have to go over the network to get it.
That's a big plus for speed-critical applications.
Absolutely. Now, the client-server approach is a bit different.
So?
In this setup, you have dedicated Hazelcast servers.
Okay.
And their whole job is just to store and manage the data and services.
Got it.
Your applications then connect to these servers as clients.
Oh, I see.
This way, you can scale your Hazelcast cluster separately from your application servers.
So you could add more servers as your data grows without having to touch the application itself.
Exactly. It's very flexible.
Nice. Now, for those clients to connect, Hazelcast provides these connectors, right?
Right. They've got clients for Java, .NET, C++, all the popular languages.
That's convenient.
And they've got other options too, like Memcache and REST for more general compatibility.
So there's a way to connect no matter what you're using.
Pretty much. They've got you covered.
All right. Now let's peek under the hood and see how Hazelcast actually organizes all this data across multiple machines.
Sure.
I saw terms like partitioning and backups mentioned.
Ah, yes, that's how they keep everything running smoothly and safely.
So tell us, how does it work?
Well, think of your entire data set.
Okay.
Hazelcast takes that and divides it into smaller chunks, all equal in size.
Okay.
These are called partitions.
All right.
And then it spreads those partitions evenly across all the machines in your cluster.
I see.
So each machine is responsible for a portion of the data.
Makes sense. And the backups are for redundancy, right?
Exactly.
Right.
Hazelcast creates copies of these partitions, and it puts them on different machines than the primary data. That way, if one machine fails, you still have a copy of the data on another machine.
So it's protected against hardware failures.
Precisely. And this whole system is dynamic.
Meaning?
If you add a new machine to the cluster or take one away, Hazelcast automatically redistributes the partitions and their backups.
To keep everything balanced.
Exactly. It's always adjusting to maintain that balance and resilience.
It's like a self-healing data system.
You could say that...
Pretty impressive.
Mhm.
Now let's dive into the tools that Hazelcast provides for actually working with this distributed data.
All right.
They call them distributed data structures and services.
Okay.
And the first one on the list is the distributed map, or IMAP.
That's a popular one.
Now it says here that it extends something called java.util.concurrent map.
Right.
So why is that significant for Java developers?
Well, if you're a Java developer and you're familiar with concurrent map, you're going to love this.
Why is that?
Because it means the IMAP offers a very similar set of operations that are thread safe, designed for concurrency.
Yeah.
So all those familiar tools, like put if absent, where you only put a value if the key doesn't already exist.
Right.
Or replace, where you only replace a value if it matches the existing one.
I see.
All those are available in the IMAP.
So it's familiar territory, but now it works in a distributed environment.
Exactly. It makes building distributed applications with Hazelcast a lot smoother for Java developers.
No need to learn a whole new set of APIs.
Nope. They can leverage their existing knowledge.
That's very convenient. Now, I'm curious about MapStore.
Okay.
What does that do for us?
MapStore is like a bridge between your fast in-memory IMAP and your external storage, like a traditional database.
I see. So it connects the in-memory world with the persistent world.
Exactly, because you want to keep your data safe, right? Even if the cluster goes down.
Right. You don't want to lose everything.
So MapStore lets you automatically read data from your database into the IMAP when it's needed.
Okay.
And it also writes any changes in the IMAP back to the database.
So it keeps everything in sync.
It does. Now, there are two main ways to do this.
Yep.
Write through and write behind.
Let's hear about this.
All right, so with write through, whenever you change something in the IMAP, like update a value or delete an entry, Hazelcast immediately writes that change to your database.
Right away.
Immediately. It doesn't wait.
Wow, so it's really in sync.
It is. It's very consistent.
But that could slow things down, couldn't it?
It can, especially if your database is a bit slow.
Right.
So that's where write behind comes in.
Okay, how's that different?
With write behind, when you make a change in the IMAP, it gets updated in memory right away.
Okay.
But the actual write to the database happens later in the background.
Ah, so it's not blocking.
Exactly. It can significantly speed up things, especially for applications that do a lot of writes.
So if I'm collecting a ton of sensor data, for example, write behind might be a good choice.
It could be. It really depends on your specific needs and how much latency you can tolerate.
I see. Now, what about MapLoader? What's its role in all this?
MapLoader is all about preloading data.
Okay, like getting the IMAP ready to go.
Exactly. It loads data from your external data store into your IMAP when a Hazelcast member starts up.
Got it.
Or when a particular key is accessed for the first time.
Oh, yeah.
You can configure it to load everything, or just a specific subset of data based on keys.
Ambi.
And you can even do lazy loading, where it only loads data when it's actually requested.
Oh, so it's on demand?
Exactly. They've got a method called load all keys that's really efficient for this.
How so?
Well, instead of one machine loading everything, it divides the work among all the members in the cluster.
So it's parallel loading?
It is, and it can really speed up the initialization process.
That makes sense. Now, near cache is mentioned as a way to make reads even faster, especially for those leap members.
Yes, near cache is a very clever trick.
Tell us about it.
So imagine you have a client application.
Okay.
And it wants to read some data from the IMAP.
Mm-hmm.
Instead of going all the way to the cluster every time, New Cache creates a local copy of the data on the client side.
It's like a mini cache right there on the client.
Exactly. And when the client needs to read that data, it checks its near cache first.
And if it's there?
Boom. It gets the data right away, no network trip required.
So it's super fast.
It is, especially for data that gets accessed a lot.
Now, you mentioned leap members.
Right. These are Hazelcast instances that are part of the cluster,
Okay.
but they don't actually store any of the main data partitions.
I see.
They might be used for running computations or something like that.
Okay.
But even though they don't hold the main data, they can still have near cache.
So they can still benefit from fast reads.
Exactly. They can access data from the cluster super quickly, even though they're not storing it themselves.
That's a clever way to utilize those light members. And I see that Hazelcast Enterprise HD has something called the native in-memory format for near cache.
That's right.
How does that improve things?
Well, it makes reads even faster.
Even faster.
Yeah, it's optimized for performance.
Makes sense. What about map interceptors? They sound like they give us a lot of control over how the map works.
They do, they're very powerful.
What can you do with them?
Well, imagine you want to do something special before or after certain map operations, like putting a value, getting a value, or removing a value.
Like adding some logging or something.
Exactly. Or maybe you want to validate the data before it's put
To
in.
make sure it's correct.
Right. Or you could trigger some other action after a value is updated.
So it's like adding hooks into the map's behavior.
It is. It gives you a lot of flexibility to customize how the map works.
Very cool. Now we've got map listeners and continuous query cache. They both seem to be about getting notified when things change in the map.
They are. They're all about reacting to events.
So what's the difference between them?
Well, with map listeners, your application can basically subscribe to certain events that happen within the IMAP. Like when an entry is added, removed, updated, or even evicted, which means it's removed because of size limits or inactivity.
I see.
You can even listen for events when the entire map is cleared or evicted.
Wow, so you can really keep track of everything that's going on.
You can. It's very useful for keeping your application in sync with the map's state.
Yeah, what about continuous query cache? How is that different?
Continuous query cache is like a super-powered map listener.
Okay, tell me more.
Instead of just listening for individual events, you can define a query, like a filter.
A filter for the data in the map.
Exactly. And then the continuous query cache will keep a local cache of all the data that matches your query.
Ah, so it's like a filtered view of the map.
It is, and it's updated automatically in real time.
So as the data in the map changes, the cache updates to reflect those changes.
Exactly. It's a very efficient way to keep track of data that meets certain criteria.
Sounds like it could be very powerful for certain applications. Finally, I see that IMAP supports transactions.
Yes, for those critical operations that need to be all or nothing.
Exactly. So what kind of guarantees does Hazelcast provide for transactional operations on the IMAP?
Hazelcast supports both one-phase and two-phase commit protocols for transactions on the IMAP.
Okay, I'm familiar with those from the database world.
Right, they work in a similar way here.
So two-phase is the default, is that right?
It is, and it offers stronger consistency, especially if a Hazelcast member fails during the commit process.
Because it makes sure all the operations within the transaction either succeed or fail together.
Exactly. It prevents the system from ending up in a weird, inconsistent state.
Makes sense. And one phase is faster, but a bit riskier.
Right. It's simpler and faster, but there's a slightly higher chance of inconsistency if something goes wrong.
I see. One thing to note here is that integrations with external data stores, like through MapStore, don't directly participate in these Hazelcast transactions.
That's right. It's something to be aware of.
Okay, so we've got a pretty good handle on the IMAP now.
We do. It's a versatile data structure.
Let's move on to the next one on the list. The distributed queue, or IQ.
All right, time for some FIFO action.
It's described as a distributed version of Java's java.util.concurrent.blocking queue.
Right, good old blocking queues, but now they're distributed.
So what are the key things we need to understand about it in this distributed context?
Well, the important thing is that it behaves just like a regular blocking queue, but it works across multiple machines.
So multiple producers can add items.
Exactly, and multiple consumers can take items.
And it all happens in a nice, orderly, first-in, first-out manner.
Precisely. It's perfect for building reliable message processing systems or coordinating tasks between different parts of your application.
I see, like a distributed work queue.
You got it. Now, you've got some configuration options here.
Like max size, which limits how big the queue can get.
Right.
And backup count, which controls how many backup copies are made.
For redundancy.
But what about empty queue? What's that all about?
That's a handy little feature for keeping things tidy.
Okay, how does it work?
Well, if a queue sits there empty for a certain amount of time, Hazelcast can automatically remove it.
So it's like a self-cleaning queue.
You could say that. It prevents the cluster from getting cluttered up with unused queues.
Makes sense, like taking out the garbage. Now, what about the distributed set, or biset? It's also a distributed version of a familiar Java collection.
Right, the java.util set.
So how does it work in the Hazelcast world?
Well, just like a regular set, it doesn't allow duplicates.
So each element is unique.
Exactly. And it doesn't care about the order of the elements. But there's a key difference. The iSet in Hazelcast is not partitioned.
Meaning?
It means that all the data in a particular iSet lives on a single partition, on a single machine.
Oh, so unlike the IMAP, the data isn't spread out across the cluster.
That's right.
So what are the implications of that?
Well, the main one is scalability.
Oh,
Because all the data for a given iSet is on one machine, The size of that set is limited by how much memory that machine has.
So it can't grow beyond the capacity of a single machine.
Exactly. So if you need to store a massive amount of unique items,
Right.
it's probably better to use multiple isets or maybe even an IMAP.
To spread the data out.
Exactly. But for smaller sets that are frequently accessed, the iset can still be a good choice.
I see. Now the ring buffer, or I-ring buffer, sounds interesting.
It's a cool one, very efficient.
It's described as a high-throughput, low-latency data structure.
Right.
For situations where you have one writer and multiple readers.
Exactly. It's perfect for that kind of scenario.
So what makes it so well-suited for that kind of workload?
Well, it's essentially a circular buffer with a fixed size that you set up front.
I see.
And you can configure how it stores data in memory using the in-memory format setting.
For controlling how the data is represented in memory.
Right. And it has these really efficient methods for adding and reading items in batches.
Batches, meaning multiple items at once.
Exactly. So instead of adding or reading one item at a time, you can do it in chunks, which is much faster.
I see. That makes sense for high-throughput scenarios. Moving on to messaging, we have topic and reliable topic, or iTopic and iReliable topic.
Ah, yes, the pub-sub duo.
They both seem to be for publish-subscribe communication, but what's the key difference between them?
Well, with iTopic, when you publish a message, it gets sent to everyone who's subscribed.
Okay, like a broadcast.
Kind of. And you can configure things like enabling statistics about the message flow.
Okay.
Or whether you want to enforce a strict ordering of messages across all the subscribers.
Interesting.
But here's the thing. iTopic doesn't guarantee delivery.
Uh-oh, that sounds risky.
It can be, especially if you're dealing with unreliable networks.
So if the network hiccups, the message might just disappear.
It might. It's a best effort delivery mechanism.
Not ideal for mission-critical stuff.
Definitely not. That's where iReliable topic comes in.
Okay. How does it guarantee delivery?
Well, it uses some clever internal mechanisms to make sure that messages are kept safe until they're actually received and acknowledged by all the subscribers.
So even if there are network problems, the messages will eventually get through.
Exactly. It's much more reliable for important messages.
That's good to know. Now, I see that you can configure how many messages are read at a time.
Right, the read batch size setting.
And there's also a setting for what happens if the topic gets overloaded with messages.
Right, the topic overload policy.
So you can control how it handles back pressure.
Precisely. Moving on to synchronization, Hazelcast provides the distributed lock, or iLock.
For making sure only one process can access a shared resource at a time.
Exactly. It's like a mutex, but it works across the entire cluster.
So multiple applications can't step on each other's toes.
Right. It prevents data corruption and race conditions.
Very important. So how does it work?
It's basically a distributed version of the java.util.concurrent.locks, lock interface in Java.
Okay, familiar territory for Java developers.
When a thread or process acquires the iLock, it gets exclusive access to whatever resource it's protecting.
And no one else can touch it until they release the lock.
Exactly. But here's a caveat. Hazelcast's iLock doesn't guarantee fairness. It means that threads might not get the lock in the order they requested it.
So there's no strict queuing.
Right. But it's still very effective for preventing concurrent access issues.
Okay. And I see there's a try-lock method, which lets you try to acquire the lock with a timeout.
Right, so you don't get stuck waiting forever.
And there's the concept of a lease time, where the lock is automatically released after a certain amount of time.
Exactly, even if the process that acquired the lock forgets to release it.
That's a good safety net to prevent deadlocks.
It is. It helps keep things moving. Now, Hazelcast also provides other distributed concurrency utilities like Semaphore and Atomic Long.
So it's bringing those familiar concurrency tools into the distributed world.
It is. iSemaphore is like a distributed version of a semaphore.
So you can control how many concurrent accesses are allowed to a resource.
Exactly. And iAtomic Long is a distributed version of java.util.concurrent.atomic.atomic long.
So you can atomically increment or decrement a long integer across the cluster.
Precisely. But keep in mind that these distributed operations involve network communication.
So they might be a bit slower than their local counterparts.
That's right. Now, what about iAtomic reference and iCountDown latch? How do those fit into the picture?
Well, iAtomic reference is like a distributed version of atomic reference.
So you can atomically set and get an object reference across the cluster.
Right.
And it has some fancy methods for atomically updating the referenced object with a function.
Okay, that sounds useful. What about iCountDown latch?
iCountDown latch is a distributed version of the regular countdown latch.
So one or more threads can wait for a certain number of operations to complete before proceeding.
Exactly. It's great for coordinating distributed workflows.
Sounds like a powerful tool. Okay, the last data structure on our list is the replicated map, or I-replicated map.
Yes, this one's a bit different.
It sounds like it takes a different approach compared to the regular partitioned IMAP.
It does. It's all about speed.
Tell us more.
So instead of dividing the data into partitions and spreading it out, the I-replicated map makes a copy of the entire map on every member of the cluster.
Wow, so everyone has a full copy.
Exactly, which means that reads are super fast.
Because the data is always right there, locally.
Precisely. But the trade-off is that writes are a bit slower.
Because the changes have to be propagated to every replica.
That's right. And the consistency model here is eventual consistency.
Meaning?
It means that after you write something, you'll see the change right away on the machine you wrote to.
Oh, good.
But other machines might see the old data for a short time until the replication catches up.
So there's a brief window of inconsistency.
There is, but it's usually very short.
Okay. And there are some configuration options for controlling how this replication works.
Right, like async fill-up, which controls how new members get their initial copy of the map.
Interesting. So it seems like the I-replicated map is a good choice if you need really fast reads and you can tolerate a little bit of eventual consistency.
Exactly. It's a trade-off, but it can be very beneficial for certain applications.
Okay, let's shift gears now and talk about how we actually interact with a Hazelcast cluster once it's up and running.
All right.
We're moving into the realm of operational and management features.
Okay.
And the first thing on our list is Hazelcast clients.
Ah, yes. The lightweight way to connect.
So what exactly are Hazelcast clients and what's their role in the architecture?
Well, imagine you have an application that needs to use the data and services provided by Hazelcast.
Okay.
But you don't want that application to be a full-fledged member of the cluster.
Because it doesn't need to store any of the main data.
Right. Maybe it just needs to read some data or execute some computations.
I see.
That's where Hazelcast clients come in.
So they're like lightweight connectors.
Exactly. They connect to the cluster and can access all the goodies without being a data storing member.
Very convenient. And Hazelcast provides these client libraries for different languages, right?
They do. They've got Java, .NET, C++, plus all the popular ones.
That's handy.
And they're usually smart clients by default.
Smart clients. What does that mean?
It means they know the topology of the cluster.
Okay.
And they can connect directly to the member that holds the data they need.
So it cuts down on network hops and makes things faster.
Exactly. But you can disable this smart behavior if you need to.
For some specific networking reason.
Right. In that case, they'll connect to a random member, and that member will route the request internally.
Okay, so there's flexibility there. Now, how do we configure these clients to connect properly and securely?
Well, you've got a whole bunch of configuration options for that. Like connection timeout, which controls how long the client will try to connect initially.
Okay.
And connection attempt limit, which sets how many times it'll retry if the connection fails.
So you can tweak how persistent it is.
Right. And then there's connection attempt period, which controls the delay between those retries.
I see. And to speed things up, you can also configure client-side near cache.
Exactly. That can make a big difference for read performance.
And of course, we can't forget about security.
Never.
So how do we configure things like authentication and SSL encryption for the client connections?
Well, you can set all that up in the client configuration.
Okay, so it's all centralized in one place.
It is. It's pretty straightforward.
That's good to know. Let's talk about serialization now.
Okay.
This is how Hazelcast converts our Java objects into a format that can be sent over the network and stored in memory.
Right. It's a crucial part of the process.
So what options do we have for serialization?
Well, you can use plain old Java serializable, which is built right into the language.
Okay, simple and familiar.
But for better performance and more control, data serializable is the way to go.
How does that work?
With data serializable, you get to define exactly how your object's fields are written and read from the network.
So you can optimize for size and efficiency.
Exactly. You can also use externalizable, which gives you even more control over the serialization process.
So you can really fine-tune things.
You can. And if you need something really custom, you can implement a stream serializer.
Wow, so there's a lot of flexibility there.
There is. You can really tailor the serialization to your specific needs.
That's great. And I see that Hazelcast already includes efficient serializers for common Java types.
Right, they've got you covered for the basics.
That's convenient. Now, one more thing about serialization. The Hazelcast instance-aware interface.
Yes, that's for objects that need to access the Hazelcast instance during serialization.
Okay, so they can interact with the cluster if they need to.
Precisely. Moving on to management and monitoring, Hazelcast provides the management center.
Ah, yes, this sounds like a powerful tool.
It is. It's like a mission control for your Hazelcast cluster.
Tell us about it.
Well, it's a web-based tool.
So you can access it from anywhere.
Exactly. And it gives you a real-time view of what's happening in your cluster.
Like what?
You can see the overall health of the cluster, the status of all the individual members, how much CPU and memory they're using, their network activity, all that good stuff.
So you can keep an eye on everything.
You can. And you can drill down into the details of your distributed data structures.
Like the IMAPs and IQs we talked about.
Exactly. You can see their sizes, how many operations are being performed on them, their latency, all the important metrics.
Very comprehensive. And I see that you can even browse the data in those structures.
You can. It's very handy for debugging.
Now, it's not just about monitoring, right?
Yeah.
You can actually manage the cluster through the management center.
That's right. You can do all sorts of things. Well, you can change the configuration of maps on the fly.
So you can tweak things without restarting the cluster.
Exactly. And you can take thread dumps from cluster members if you need to troubleshoot something.
Ah, for debugging those tricky concurrency issues.
Precisely. You can even execute scripts on the members, like JavaScript or Groovy scripts.
Wow, so it's pretty powerful.
It is. You can do a lot with it. You can also set up alerts, manage users, and integrate with other monitoring tools like New Relic and AppDynamics.
So it's really a one-stop shop for managing your Hazelcast deployment.
Pretty much. And if you need to access this monitoring information programmatically, they've got a clustered REST API.
So you can integrate it into your own tools and dashboards.